is that these are somehow tame, which behave like integers in some way. Well, this is, of course, a very vague description. And there's something like a 1,000 different ways to define these things. There's whole books of them. And these definitions are sort of surprising that some of them are equivalent. And so it's a very robust notion of tameness. And often in the various contexts where this definition shows up, once you can prove something for Z, you can prove it for all immutable ones. So this is, so I can only really give you an impression of what these things are like. So the plan for today is to go through 4 of the common definitions of this thing. And then maybe if there's a time at the end, I'll state some theorem that says very precisely that these things are like C. Okay, so let's get started. First way of defining these things is via Følner's condition. So, so a useful fact about the integers that for any finite subset of Z, if you go out far enough, then the interval of length n is going to be more or less invariant under translations from this finite set. So a plus minus n, n symmetric difference itself divided by size of this interval. Oh, yes, I should also say for any epsilon greater than 0 in finite set. This proportion is less than epsilon. Great, so picture, we have the integers, they look like a line, and we have some finite set lives inside of here. There's some very big interval where if we perturb the interval by this finite set, this boundary is small. And this is incredibly useful in ways that maybe aren't immediately apparent. Sorry. And further, these sets with small boundary can be pushed onto the dynamics. Yes. So probably put it here. So maybe a theorem. This is called the Rocklin lemma. So if Z acts on some probability space, and for all n, maybe I want to say freely as well, but for all n, and a measurable, and A has the same measure as A. Measure A. Right. So Z acts freely on some probability space in a way that measures are preserved. So it's called a PMP action, a probability measure preserving action. Then for any n and epsilon, there's set B subset of X measurable, so that following hold, the intersection of I dot B with J dot B is empty for I and J less than n distinct. And the translates of B up through n cover almost everything. Okay. So again, picture a space ends up looking like our set B, along with all of the translates of it under our action of the integers, and then some small leftover bit. And so we understand what the action is doing on sort of everywhere inside of here. It just moves you over to the next blob. And where there's only mysteries here at the boundary, which should be small. Okay.
What does the first condition say? Could you just restate it?
Yeah, this says that if you translate by I and by J for different I and J, you get disjoint sets. Okay, maybe let's see how much time I have. Great. Okay, so let me maybe rapidly sketch one use of this machinery in action. So here is a theorem. So for let's say S and T automorphisms of some probability space, a periodic. Okay, so a periodic automorphism of measure space, that's just a sort of measure theoretic bijection from the space to itself that never wraps around. So this is same thing as saying free action of Z, PMP action. There are UN, also automorphisms. So that for a subset of X measurable, S and the conjugation of T by these UNs asymptotically do the same thing to A. So what does that mean? The measure of the symmetric difference of S of A and UN T UN inverse of A goes to 0. So any two actions of Z, if you like, are three PMP actions are approximately conjugate in some sense. And the proof, when we take that picture, I draw it twice. So this is what S looks like for some. Sorry. Yeah, so what S looks like. Can find some B that gives us this picture. And this is what T looks like. 1, 2, 3. That's good. Okay. Right. And so we understand what S is doing sort of all along this sequence and what T is doing, S is doing here and T is doing here. And so we can just map this set to this set using some measure preserving bijection, and then that forces our hand everywhere else. So U sort of lines up here. And then if we want to measure, what's happening on some general set, it will intersect all of these in some place. And the only place where we land inside of the symmetric difference will be on the boundary over here, and we know that that will be small. So that is a very rough sketch as to why this theory is true.
You also have to conjugate the second one to make sure it's equivariant, right?
Yeah. Once you know what you're doing here, that sort of forces your hand everywhere else. Yeah.
Okay.
Yeah. Good questions. Okay. Okay. So for our first definition of amenability, we're just going to abstract this notion. So definition. So for gamma accountable group, epsilon greater than 0, a subset of gamma finite, say S subset of gamma finite set is a epsilon Følner. We form this ratio a dot S symmetric difference S divided by x of S. This is less than epsilon. And gamma satisfies Følner's condition for all a epsilon. There exists S, so that S is a epsilon Følner. Oh, this doesn't move. Can you all see over here? Okay. Okay. Gosh. Okay, I'll leave that there. Okay, so some examples. Okay, so of course Z is Følner as witnessed by this useful fact here. Finite groups. Right. If you want to find a Følner set, you can just take the entire group if it happens to be finite. If gamma and delta satisfy Følner's condition, then so does any semi-direct product of them. Right. This I suppose is an exercise, but roughly this thing looks like some kind of Cartesian product of these two, and so if you have Følner sets here, you can make a big Følner rectangle here. So, for instance, this means all solvable groups are going to be satisfy Følner's condition. If you keep taking your groups and extending them, you get these big class of so-called elementary amenable groups. Okay. If gamma has sub-exponential growth, then gamma satisfies Følner's condition. Okay, this chalk is disintegrating.
You mean the balls in gamma?
Yeah, right. So when I say sub-exponential growth, I mean if you look at you take some generating set for gamma and you look at the size of that set, the size of that set squared, the size of the set to the third, and so on. If that grows sub-exponentially, then this group has to satisfy Følner's conditions. The reason is that if you look at these balls, eventually they have to have small boundary. Otherwise they would grow exponentially. Okay. Maybe something I should say explicitly. Gamma is finitely generated, say by some set E, and gamma has E epsilon Følner sets for all epsilon. Then gamma satisfies Følner's condition. Okay, so if E is a finite Ewing set for gamma, you can form a Cayley graph. And then this is some kind of isoparametric condition in the Cayley graph. All right. So that's Følner's condition, which is one of our many definitions of amenability. Yes, I've confused myself about where I would go.
Josh has a question.
Oh, yes.
Yeah, just because you mentioned solvable things, do you want to include increasing union?
Yeah, I was going to say.
Oh, yeah, yes. Sorry, I should do that. Right. If gamma is an increasing union of gamma I, with each gamma I, each gamma I satisfying Følner's condition. So does gamma. Yes, thank you. Right. Right, because if you have a finite set, it lives inside of some finite index, and therefore you can find Følner sets there. To work in the whole group. Okay. And I should know that, right, so I mentioned over there that we can push these Følner sets onto the dynamics of our group. And this is also true for general amenable groups, although it is harder to prove, in fact, even harder to state. But so here's an exercise, look up Ornstein Weiss.
Suppose the switch on us and you went from finally generated groups to non-finally generated groups?
No, I only assume finitely generated here.
Maybe he means like this with these increasing unions, you leave the finitely generated world.
Yeah, that's true. But the definition I gave of a of this Følner condition is already makes sense for not necessarily finitely generated groups. Right. Okay, where's ways and generalize. Suppose a proposition I just erased. Yeah, word mess, man. Generalize approximate conjugacy.
Also, Rothen's lemma, which you haven't erased, so you can use that.
Yes. Yes. Great. I think I said aloud, but this Ornstein voice is the sort of generalized version of this Rothen lemma. Okay. And then because it will be useful when we try to talk about amenability of equivalence relations, whatever that means. Let me go ahead and mention a slight variation on Følner's condition, which is Reiter's condition, which is a sort of linearized version of Følner's condition. So a function in L1 of gamma, right? So this is gamma index sequences which are summable. Yes.
Sorry, what is this an example of?
What is what an example? This is an exercise.
Ah,
Yeah. EG is example, EX is exercise. Sorry.
And what does it say before Reiter's condition?
Oh, 1A. Okay. Other questions about my handwriting? Yeah. Do feel free to shout about that. Okay. So F is an L1 of gamma is a epsilon Reiter function. Got some conditions. So it needs to be finitely supported, meaning it's zero almost everywhere. It needs to be positive. So all of its values are non-negative reals. It's just a non-negative, not positive, I guess. And it needs to, again, have some kind of approximate invariance. So in this case, we'll say A dot F minus F has one norm less than epsilon. Right. Okay. And again, we can introduce Reiter's condition. Yes, I'll erase this. It satisfies Reiter's condition.
What is A and what is A vector?
So this is a finite subset of gamma, just as it was over here. And this, I guess you can, if you prefer, this is the sum over gamma in a gamma dot F over the size of A. Yes. Yes. So it's Reiter's condition if for all epsilon E is some epsilon Reiter function.
Right, just in case the question was what is gamma dot F, maybe.
Oh, right. Yes. Right. So F was in L1 of gamma. Gamma acts on L1 of gamma by shifting indices. Yeah. Precomposing with the automorphism of gamma acting on itself.
and it doesn't matter whether we want like gamma inverse or gamma, like is it f of gamma times x or is it f of gamma inverse? So I think this was clear.
Right. So
That doesn't.
Probably doesn't matter. It won't matter for the
Won't matter.
but if you want an action.
yeah. Yes. Inverse. Yes. Right. Yeah. It's whatever it needs to be to make this an action. Yeah. Okay. Good. Okay. Right. So F is right. Yes. And so proposition gamma satisfies Reiter condition if and only if gamma satisfies Følner's condition. Proof. Okay. So if you satisfy Følner's condition, you satisfy Reiter's condition. that's true because if you take the characteristic function of a Følner set, it'll be a Reiter function. Or S, I guess. And the other direction is a somewhat standard trick for this kind of equivalence where we're given some kind of function and we want to cook up a set. And so we can give what's called a layer cake decomposition of our function and then take some support of a layer. So F has I should say it's going to be a very sketchy proof. Layer cake decomposition. Which I guess I will do up here. So F, right. So what does that look like? It's finally supported, so it sort of has some mass here and some mass here, some mass here and some mass here. So we can chop this mass up into layers, like so. Right. So this bottom layer is the full support. Then function jumps up and has support here for all of its, not lowest value points, and here for all of its not second lowest value points, and here for all of its highest value points. Okay. So F can be decomposed into blocks of mass sitting in layers over some smaller supports. Okay, and then you can check if F is sufficiently Reiter. If it's a Reiter function for A and epsilon, possibly bigger than the A and epsilon that's our target, then some layer is sufficiently Følner. Right. And that's just sort of playing around with some L1 estimates, and I won't, bore you with all of that. But this is the important picture to have.
Pigeonhole principle.
Yeah. Okay. Good. Okay. So that's one pair of conditions for amenability, is Reiter condition and this Følner condition. Another one, which is measures and means. So as a proposition, if gamma satisfies Følner's condition and gamma acts on X, a compact space, the action is continuous, then there is a gamma invariant measured on S. Yeah, right. This workshop is about measured group theories. So we'd like to have some measures floating around, and if the group is amenable, then we get one, and that's nice.
Measure it in probability measure.
Yes. Sure. Otherwise, that's trivial. Isn't it? Let me very quickly sketch an argument for this. So proof sketch. Okay, so good. Delta be some delta mass on X. So you pick a point and put all your measure on that point, then let delta n be, okay, we take this point mass, we push it around by some elements of gamma, then we average out over some set of translates with S A n epsilon with S. Let's do this with Sn eventually A epsilon Følner or a subset of gamma finite and epsilon greater than 0. Okay, Right. So again, we take some sequence of sets that grow bigger and bigger and are eventually as Følner as we like. And we push around our mass by these Følner sets and take an average over all the translates. Okay. Then we would like to take some kind of limit of these things. And like, yes, we're working with a compact topological space. And so the space of measures with the weak topology is compact. So take mu, any limit of a subsequence and the weak topology. Yes, I think I also need X to be, I mean, I think I just said compact space. I mean, compact, let's say Hausdorff metrizable equivalence space. So something where we have sequential compactness for the weak topology. Okay, and this will work. Right, so if f is a continuous function on X. Right, so the weak topology is generated by integrating against these kinds of test functions. And gamma is in gamma, then the integral of f against delta n differs from the integral of f against gamma f against delta n. Will be bounded by something times the size of the boundary of this Følner set. So Sn delta gamma Sn over Sn. And because we chose these things to go to zero, these will have to go to zero. And so any limit of these things will be invariant.
Sorry, wait, CX.
What is a continuous function on X? Yeah, right. The weak topology is a topology where things converge if their integrals against continuous functions converge. So this is the sort of test you need to do to understand weak convergence. So, slightly strange question. What about the action of gamma acting on itself by multiplication? There's not going to be any invariant probability measures here because this is a countable set. But we can get something that's sort of close. So definition, a mean on gamma is some mu from the power set, the full power set of gamma to 0, 1, such that that is closed. So that, okay, what happens? The measure of the entire group has to be 1. It has to be finitely additive. Meaning, if you measure a disjoint union of sets, you have to get the sum of their measures. And it has to be invariant. So measure of gamma dot A is the measure of A. Those are the three properties of a mean. And a group gamma is amenable if you can put a mean on it. And proposition, if gamma satisfies Følner's condition, gamma is amenable. Okay. Right. This is the definition where the name amenable comes from, because you can put a mean on them. It's a very funny pun, and you should all laugh. And I can go ahead and sketch a proof of this. Let mu n of A be, and we're just going to measure against a Følner sequence, size of A intersect Sn over size of Sn, or Sn Følner sequence, a sequence like we had before, which is eventually Følner for any set you like. And we want to take a limit of these kinds of objects. So these are functions on a power set of a group. So, gosh, what are we going to do? So take, for instance, an ultra limit meter to the limit along some ultra filter UN for some non-principal ultra filter. Or if you're not familiar with these ultra filters, I would suggest you read into them. But you can also look at a compact space of 0, 1 to the power set and try to find some limit point there. Argue by the phi intersection property. Okay. So those are measures and means. Running out of time, so maybe might be the last one. This is paradoxicality, which is, I guess, rather a characterization for non-amenability. So,
Riley,
yes.
you didn't say that these are equivalent. You just took one direction.
Yeah. Right. So I'm going to go through this to prove they're equivalent.
Okay.
Yeah.
Okay. Sorry.
Yeah. Right. So far we have Følner's condition implies amenability. And then there's going to be a third thing that follows from amenability and it implies Følner's condition. It has to do with these paradoxes. So, right. So consider F2. This is the free group on 2 generators. It looks like a tree. Right. So this is some generator A, this is some generator B, and anywhere you go, you end up somewhere different. So let's define some sets. Let's say this is A, and this is C, and it'd be nice if I had another color, but oh well. And this is B, and this is D. Okay, so A is all of the strings which start with A. C is all the strings which start with A inverse, similarly for B and D. These are all disjoint, and notice that F2 is equal to A times C union A, and it's also equal to B times D union B. Right. If I translate all of these things by A, they cover everything that doesn't start with A. And likewise for D. So we can write our group as, we have 2 copies of our group as translates of disjoint subsets of our group. Our group can cover itself twice. This is paradoxical. And this is sort of what's underlying the Bonnet-Tarski paradox, if you're familiar with that. You can find some nice actions of F2 on a sphere, and then use this sort of strange decomposition to take a sphere and break it up and move it around by isometries to get 2 spheres. It's spooky. Okay, so gamma is paradoxical if there are A1 up through AN, B1 up through BM, subset of gamma disjoint, and gamma 1 up through gamma n, delta 1 up through delta m, elements of gamma, so that gamma is the union of the translates. So,
so A's are disjoint from B's.
yes, yes. All of these sets are all pairwise disjoint. They're disjoint from each other, and their A's are disjoint from B's, A's are disjoint from A's. Yeah, like this picture up here. Okay, so proposition. Amenable implies not paradoxical. So proof 1 is not equal to 2. Right? You measured this side and you measured this side. This gives you 2 and this gives you 1, and that's bad. Right. So in particular, F2 is non-amenable. That's our first non-amenable group. It's surprisingly hard to find examples that don't contain F2 or something like it, but they do exist. Okay, and then proposition. All of these things are in fact equivalent, and this actually probably deserves the word name theorem. I think it's due to Théories. So theorem. Not paradoxical implies Følner. So amenable implies not paradoxical implies Følner, Følner implies amenable. These are all the same thing. A beautiful world.
So can I ask
Yeah.
maybe a philosophical question? So the proof that Følner implies amenability relies on the existence of the non-principal property there.
Or some kind of compactness, yeah.
What if we drop the axiom choice? Like this does depend on the axiom choice. What if we drop it? Are the definitions still equivalent?
Probably not.
Okay.
Axiom of choice is stronger than alpha filters. So what if
Well, yeah.
the alpha filters
It's
also,
not-
then
Yeah. And if under an L of R under AD, things get weird, maybe. Right. Yeah, and this proof is also going to use an ultra filter or something like it. Yeah. So Følner's condition is sort of it's at the heart of things. The thing we don't need choice. Okay. So paradoxical by Følner. Right. So we're going to do this by contraposition. Suppose gamma is not Følner. And we might as well assume it's finally generated. Let's say by E. Then note that for all A dot E is at least some constant times the size of E. Sorry, size of A. It's a subset of gamma. Right, because otherwise, for some C, so maybe it exists C greater than 1, right? There's some C greater than 1, so that anytime you multiply a set A by E, it grows by this constant factor, bounded away from 1. Because otherwise, we could find Følner sets, right?
sorry, Ryan, what is this without loss of general? Like, you're assuming finitely generated because you can, but
Yeah.
So I just didn't read what you wrote before gamma.
So we may assume gamma
we
is
may
finitely
assume,
generated.
okay.
Yeah. We may assume, yes. Weapons of mass assumption. Okay, so right. Okay, and then by replacing E with E to some large power, we may assume C is at least 2. Okay, and then we're going to form a graph. Okay, consider graph. We have copy of gamma on the left, copy of gamma on the right, and another copy of gamma on the right. We're going to tag these two copies 0 and 1. And we connect every vertex on the left to its images under E in both copies on the right. Great. So edges come from a generating set E, but there are 2 copies on the right. Okay, and note gamma is paradoxical if and only if this graph has a matching of the right-hand side into the left-hand side. Right. Whereas a matching means that every vertex here can pick out some group element and some translate so that no 2 of these copies on the right pick out the same copy on the left. In vertex on the left. It's the same thing as saying we can break up our group into that many pieces and then translate them to get 2 copies. Okay. And why does this group have, why does this graph have such a matching? So theorem. This is essentially due to Hall, right? He proved it in the finite case, but you can get to the infinite case by some kind of ultrafilter argument, compactness argument. G has a matching, so G locally finite has maybe bipartite with has matching of its right hand side into its left hand side, but only if for all a subset of the right hand side finite, the size of the neighborhood of A is equal to, or is greater than equal to the size of A. So Paul's condition gives us, for locally finite bipartite graphs, a way to check if there's a matching. And it's just, we need to take a set on the right-hand side and look at its neighborhood, look at the size of its neighborhood. And if that's bigger than or equal to, then we get a matching. Why does that hold here? Well, if we have a set on the right-hand side, I mean, we may as well assume it's the same, set at the top and the bottom. The number of neighbors on the left-hand side, that is going to be E times A, that has at least twice the measure of what's going on in one copy. And so it has to be at least twice the measure of what's happening in our whole set on the right-hand side. So I can write that down. So fix a subset of right-hand side of G is over there. We may so say A intersect gamma cross 0 is bigger than the part of it in the top is bigger than or equal to the part of it in the bottom. That's bad inequality, but oh well. Then and let's call this A0. Then the neighborhood of A, that's bigger than or equal to the size of E dot A0, which is at least twice the size of A0, is bigger than or equal to the size of A.
Your E is symmetric.
Yeah, symmetric. Generating a set, let's say, symmetric. Okay.
Sorry. So here you seem to only have used that it has super exponential growth, or like it has exponential growth. Sorry. What else is used?
Well, no, I need to know that for any set over here, when I take its boundary, it gets bigger, not just for
Just
the
for
balls.
balls. Right. Right. Okay. So I guess that's the subtle difference between non-amenable groups and like exponential growth.
Yeah. So that not all sets are spheres. Okay. How much time do I have more time? Am I done?
No, 3 minutes.
3 minutes. Okay. I'll try to state something in 3 minutes. Okay. So yeah, let me just state one last thing. Okay. Maybe first. So this tells us that all the three of these conditions are equivalent. So we end with something about orbit equivalence, just to sort of I don't know, foreshadow some other stuff in these workshops. So definition. Okay, so we have two different groups acting on two different measure spaces in some PMP way. Okay, so these are probability measure preserving actions. Then let's say this is A and this is B. Say A is orbit equivalent to B if there is some F from X to Y, isomorphism of measure spaces, which turns the orbits of A into the orbits of B. So that F of gamma dot X, little x, is equal to delta of F of little x for almost every x. Okay. Right. So Right, so this is a map that turns orbits of this action to orbits of this action, and it has to be bijection. And the theorem is that this is one way of making precise this claim that these groups are all like Z. So theorem, every action of every PMP action of an amenable group is orbit equivalent to an action of Z. So we're saying this, if I give you a PMP action of an amenable group, then there's some way of cooking up an ordering of the orbits so that each orbit in this order looks like a copy of Z. Okay. This is,
Credit on Ornstein Weiss.
yes, yeah, Ornstein Weiss.
Did you build a modification?
Yeah, I mean, yeah, they might have just had it for free, but you can handle other stuff pretty straightforwardly. Okay. Okay, so right, this is very quick, rapid survey to amenable groups. Turns out they're all secretly Z. If you squint your eyes. Thanks for listening.
This one. Okay. Any questions for Riley?
That has to be infinite.
Oh, yeah.
Well, no, I mean,
I
if
just-
it's finite, then it's still an action of Z. It's just a very degenerate action, sort of cyclic.
He didn't write free
Yeah.
action, so it can be a cyclic action of Z. Other questions? Oh, I have one.
Mhm.
Maybe can you write what's not 5, meaning Dave van Neumann?
Oh, yeah. What's not right? So
I mean, what's not equivalent?
yeah, right. So there was problem. So the von Neumann day problem. So does every non-amenable group have a non-abelian free subgroup? Non-abelian free group. And the answer is no, and that's pretty difficult. You need to have, but most solutions use some heavy machinery from geometric group theory or combinatorial group theory. But in some sense, it's morally true. If you have an action, for instance, of a non-amenable group, you can find an action of a free group that lives inside of it in various nice ways. So lots of interesting things to explore there.
I guess, yeah.
One more small question. Roughly, what were the years or decades when these ideas reached a crystal form? Roughly.
So most of these equivalents, I think, are due to Tarski sometime in maybe the 40s. But amenability was started, I think, with the measure theoretic definition by von Neumann a little bit before then. I think. Yeah.
29.
29. Okay. Thank you.
Ornstein Weiss is
What?
Ornstein Weiss is
Oh yeah, Ornstein Weiss, right. So and then people really started understanding these things, understanding orbit equivalence, understanding the sort of generalized rock dilemmas and the how useful amenability is, maybe, I don't know, the 80s. 80, yeah.
Other questions?
Maybe just a comment. I want to comment on von Neumann.
Mhm.
So in his article, he explained it was the time when they discovered this Tarski paradox.
Mhm.
And in his introduction, he says, okay, one usually says that when it passes from dimension 2 to dimension 3, the space changes in nature. I will explain to you that it is not a space, but it's group of isometry. And the reason is one in dimension 2 is amenable, and in dimension 3 it is not.
Thanks, Damian. Okay, if no other questions or more stories, we'll thank Riley again.